All right, let's fire up the VM. Good. Oh, I want to reset my color theme back to my dark theme. I got a bit restless with my color theme yesterday. So we were using... Oh god, what was I using? I think it was IU. Nope, I don't recognize the color. Wasn't Dracula? Eve, maybe? Yeah, that's better. Okay, so first point of call is we've got some code that we're calling assembly from C directly using inline assembly. Hi Tay, how you doing? Oh, you followed me whilst I wasn't streaming, so thank you for that. And thank you for showing up. So we hacked a bit of a assembly into C here, and it's not the correct way to do this. So we're going to figure out today how we write assembly code in a .s file and then call that from C and somehow jump back from assembly over into C land. Gosh, it's going to be a bit tricky because I don't know what I'm doing. But we have examples and we're going to use some tutorials to kind of guide me through. So let me know if the music's too loud too, because it's kind of the middle of the day. I'm playing something a bit more upbeat than lo-fi. Oh, you're going to try and stream too? That's awesome. Yeah, OBS is quite simple to figure out once you get its layers and stuff. So you shouldn't have a problem doing that. I'm just going to call this ISR.s for now, because I know it's going to be the interrupt service routine. Now, syntax. Hello world. S file in C. Because what I've got to be careful of is the addresses of the functions that I'm defining. I've got a feeling ChatGPT might be able to help here than me hunting for this information. You're a blind Twitch streamer? Oh, wow. Making a markdown editor in Python. Music volume is good. Okay, good to know. Thank you. So well, my question just got absolutely nuked. Let's bring it over here. How can I call assembly function from C using an .s file, and inside the .s file call a C function? So I need to understand, yeah, exactly what its point, how the linker is going to resolve these addresses and names. So we mark a label as global. We define a function found in C as an external, and then we can call that name. Okay, well, that's simple. Easy. All right. So global, let's call it ISR handler. And then we'll have ISR handler. Excuse me. So our ISR handler is going to do this stuff. Which do we need this in the percent sign, I wonder? We do. Okay, so I can just nuke all of this stuff. And then nuke this guy. So we also need to define the external ISR handler, which is going to be in... I guess this is going to be handle keyboard for now. Which is kind of lame, but it is what it is for now. So then we can call handle keyboard. And then we can do our other stuff, which is the restore. Yeah, that was way easier than I thought it was. I thought we would have to do some clever compilation scripting. But it looks like the C compiler is just going to let me feed in the assembly source. As long as it's labeled so it knows where to use that label name as a function call. That's cool. Really cool. Let's get rid of these extra percent signs. Do we support comments in assembly? We do. I can't remember what the comment token is. Is it //? No, it's the £. So we need to do a CLD there because I need to make a note of this too. C functions, expect CLD instruction, can't remember what this is called, direction flag. Okay. So that makes the call, then restore the general registers and return. Direct queue. Still don't know what that add 8's doing though. I've got a feeling that's doing byte alignment or memory alignment somehow. Okay, so we've got global ISR handler, an extern handle keyboard. So now how would I get... Well, I need to change this. So we're not doing that anymore. Do we need to... Oh, that's a memory write, so I don't need to do that in assembly. That's fine. I want to figure out how to send the vector into this function too. Like, I know the vector number is on the stack, but I don't know how in assembly to access that. I can probably, like, push or add bytes to the stack pointer to walk down it and then push that into a register and then pass that to the function. GPT is going to save me here. It's guiding me. So this is what confuses me a little. For the first 6 integer or pointer arguments, use the RDI, SI, DX, RCX, R8, and R9 registers. If there are more than 6 arguments, the rest will be passed on the stack. Oh, I had no idea. That's a good reason to never have more than 6 parameters on a function. Maybe. So you don't have to do stack manipulation. So floating point numbers use different registers. Some calling conventions require specific stack alignment. For instance, the system v AMD 6 TBI requires a stack to be 16 aligned before calling. Okay. This is what it feels like. Okay, is this enough? No. So when I registered this here, we want to register the ISR handler. Now C's not going to know what this is, so how do I... Okay, yeah, we need to extern this function. ISR handler. And then it's up to the linker to wire those up, so this should be fine. That's an external in C. We're jumping to it. Okay, and then we read, we do the Q stuff, we do the ACK on the LAPIC. Then we restore registers and we do an IREC Q. Okay. That's what it feels like. And the reason we need the timer today is because we've got some performance problems already inside of our terminal code that I want to somehow time and understand where the bug is coming from. All right, I think everything's in place. If we get a compile, that's great. Bad register name, sure. Bad value. Failed to set dynamic section sizes. Relocation against undefined symbol R9 can be used when making a pi object. Recompile with fpi. Against symbol R9. Oh. There we go. What a weird error message. Holy balls, we should get... Everything should work then, so let's give that a run. Let's see if everything's working fine. And no, we faulted. No! Then the question is now, at what point did we fault? Had a feeling it wasn't going to be that simple. So that's where we got the key press. Interrupt 28. We got this exception. I need to bring up the software development manual for this, I think. A, and then programmer calc, let's see, 0. Decimal 13. All right. Interrupt general protection fault. Okay, it's the first time I've actually generated a general protection fault, so we've got to figure out from this exception stack trace what went wrong. So can I trust that the RIP is correct? Actually, can we break it down maybe? I'm wondering... Serial. Oh, for COM1, please. What is COM port 1? That address. So again, don't know assembly syntax, so we're gonna have to Google this. Okay, Chatty, what did you suggest? Load the port number into DX, load the data into AL, and then out. And then move into AL. I mean, can I just write a bunch of characters? Okay, debug print. I guess that's enough for now. I want to see if we made it into the ISR handler. Now I'm beginning to wonder if what we registered in the IDT is a bit trashed. I wonder if there needs to be some kind of... Oh. Does it need to be mapped into the right space? So let me just check how Lyra does it. So it's got a function here. And this one. Oh, they're using a line 8. Hmm. So when they register the... This macro expands into a bunch of functions, so... An array of functions. Okay, this one's maybe easier. So the panic IPI entry, an extern void. It's been passed the register handler as a normal address. It's not been translated. And then how's that defined? It's clearing interrupts. I don't know what this lock does. Oh, I guess here is what defines the array. Repeats 256 times. End repeat. Okay. That kind of makes sense. Thunk address. Maybe we can debug on the IDT. Maybe there's something in here. That's going to complain now because it doesn't have serial H. We'll have to bring that in. All right. Bit of a long stretch because that's quite kind of a reach to put a log that far down the line. Oh, wait. Operand size mismatch. I didn't notice that. Is it because I'm in 64-bit that I need to use these 64-bit registers? Add register name RAL. Can I do Rex? Operand size mismatch. Does it want 32-bit registers? Is that the problem? So it's 16-bit. So I can do AL, which is the lower of the AX 32-bit register. And then use AL. Try that. Nope. Still doesn't like it. Um, code still produces the error. Oh, I'm so stupid. Move into DX3 F8, move into AL FF, out onto the DX AL. Why do you not like me? Mm-hmm. So the percent sign means that it's AT&T syntax. Out B for an 8-bit data transfer, out W for a word. I see. AL DX. Move into AL. Put into DX the port number. Okay, that worked. Okay. So we check the log. And we didn't get a character right in between that line and this line. So we didn't get the function in the IDT. Right? Device gates, keyboard vector, set gate, ISR handler. That's this. I mean, I noticed Lyra likes putting void in between the brackets. Does that make a difference? No. Okay, so we're not getting into the handler. Let's be a bit clever here and let's dump out a log for what we're doing with the IDT. IDT set gate. Let's do %d. So it's the vector number and the handler address. All right, now we can at least see what we're putting into the IDT. So we're putting into that address 272D. And now what we can do is an object dump, which I should really, since this thingy is not working, I'm going to make this a specific run command. Called dump. Nothing to be done. There we go. Just to prove that's working, let's kill that file. Yep. All right. So now let's go to our address. So we're at this address here. Whoops. Boop. Which is the... Here it is. So it's jumping right here. And that's doing our serial right, and then our stack pushes. So, why didn't it do the right though? I just want to look up that instruction because it seems to have flipped. Output to a port. First operand is the port number. Dude. I knew that was a bit screwed up. Type mismatch for out. Okay, well, how about we just switch the values then? Put you there and you in there, right? What's that? Okay, that built. All right, we faulted. Did we get a character in the log? We did not, so we didn't get the right. That's interesting. That is very interesting. Okay, I've got another way of debugging this. What if we just tell somebody on my Discord once told me how I can cause a breakpoint. It was an interrupt call. Int 3. Can I just do that? There. Vector 3. We did it. We caused a fault. Right, so we are definitely inside of our ISR handler. Like 100% we are. So why is it having a problem calling that function? Oh, it's setting the segments. That's my problem. Is that my problem? I'm just going to go pee. He's back in a second. Hello, I am back. Sorry about that. So there's some shenanigans going on. I think we've got to do a bit more before we can jump to the C function. Well, hold on a second. No. We can just... What am I talking about? We can just... Let's look at things in a bit more fine detail. I'm missing a trick here. Yep, we faulted. Lovely. So... 2771. Make dump. And we'll fast forward to there. It's the IREC queue that died. Okay, this is what I wanted to confirm though. I wanted to confirm whether it actually did make the call into that location. So what are our segments set to? So our segments, if we go back to the IDT, I'm sure I made a note somewhere about having to pass. Oh no, it's the GDT, not the... First entry, second entry. Code segment. There. Code segment is the second entry. What? Oh, because the first entry is reserved. Null, first, second. So this is code segment. And the data segment. So the extra segment is set to the data. The stack is on the data. Data is on 10, FS is on 10, GS is on 10. Code segment is set to 8. Okay, that checks out fine. It's just the IREC queue, it's dying. Why would it be dying? There mustn't be relevant things on the stack for it to die. Maybe I take this off. Maybe that's my problem. It was my problem! Oh my god! It works! We did it! We've done it. I'm not sure why those 8 bytes were on the RSP. I think that's to do with Lyra fucking about with putting more stuff on the stack than we do. And it probably had to align it, but... Oh my god, we've jumped in and out of assembly and we've called a C function. Let's go. Confidence plus equals 1. I think I can get rid of those interrupt gates. So my question now would be, so this is the vector for handling the keyboard, though. It's not the vector that, or should I say it's not the routine that's handling like all the generic exceptions. So it's not doing my handle interrupt, should I say. I don't know if I need to change that though, because that's pretty... It's a big death hang. So I probably don't need to touch that one. Other than we are faulting, it would be nice to get the vector. I wonder if ChatGPT is clever enough to understand that context. That would impress me. How can I add the ability to receive the vector that generated the fault in this code? You need to modify the signature to accept an argument that represents the vector. Additionally, you'll have to ensure the interrupt handling infrastructure passes the fault vector to this function when the thingy occurs. I mean, I don't think we get it for free. Let me think about this. If you've... The data is on the stack. It's not necessarily on the function parameter registers. So to receive that vector on this function call, you would have to grab the data off the stack and put it onto the function parameter registers. It's probably a problem for another day, because it doesn't really affect me right now. Like, it's not a problem, but I've definitely made a mental note of wanting to do that. So we're back to the problem with our terminal having delay, which kind of sucks. I just noticed something too. How on earth did the word hello get interpreted? Oh, that's another bug. Okay. That's just my string comparison bug. That's no problem. I can fix that some other time. Okay, I think it's time. Let me commit that to... There we go. Okay, let's get rid of this. I want to put the keyboard vector back down to its original location, which is 32. Da, 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 da. Okay, that still works. Do, do, do. I think it's time for the timer. Weird. Okay, so the goal with the high efficiency interrupt flip timer is going to be to see if we can get a one-shot interrupt from it, at least, and program it in the IDT. That's going to be a good starting point. So we'll bring up the docs for doing this, which is the HPET timer doc, which is this guy. Do, 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 do. All right, let's go in. Full steam ahead. Step 1. How do we initialize the timer? Hardware overview, register model overview, memory map. Oh, I know. We were doing in the APIC, we were deserializing, or is it in the ACPI? Yeah, we were deserializing the HPET structure. What I wanted to do here was get the address of it. So let's just cast this description pointer to that one. Why are you not recognizing the struct name? Because I'm not using the word struct, because I'm silly. Now the address should come here. We'll dump these variables too. We've got comparator count. And we've got the counter size. What else have we got? Description, hardware rev ID, HPET number, minimum tick, page protection, PCI vendor ID reserved. Let's dump the address. And then let's enable that function call here. That needs a new line. Did I turn off the logging in the IDT? I did. Okay. Pretty sure I just saw an error in the compile. Yep. Implicit declaration, did you mean pass AMDT? No, you fool. Too many files open again. Let's just bring this guy up above that function. That's the one pet peeve about C, is the pre-declaration of function names. Kprintf. All right. Let's see if we get that in the log. Hello there, Neg. How you doing? Alrighty, so we've got the right variables, so we're at the right position. It looks like the address is already in the higher half. I think. No, it doesn't look like it actually. Where is that address, I wonder? Wait, there surely isn't going to be... Yeah, that probably needs offsetting with the higher half address because that is... Seems wild though. Okay, that might be a first problem, but we'll hit that when we initialize the HPET. Okay, let's save a pointer to that table. And then we'll dump those. And then I think we'll just put this in its own file. Let's do that, and then we'll have its own initialization then. Let's grab the copyright. Standard boilerplate stuff. Void HPET init. Then we'll give this a source file. HPT. Every time I see that comment, it irritates me, so I've just finally got rid of it. So we'll grab this. We'll certainly need standard int. And then need str as well. And let's just throw a little thing in the log just to say we've reached there. And then we'll add this to the kernel startup. Just over here. So keyboard. Let's initialize the timer here because that needs to come before keyboard stuff. All right, let's test the wiring. Passing HPET, HPET address comparator, counter size, HPET initializing. Okay. All right, back to the dock. How do we initialize the timer? Register definitions. Register overview programming requirements. Page 10. What is programming requirements? Oh, what I also want to bring up too is the OS dev for this. because they've kind of weeded out all the unnecessary reserved stuff in the document. So might be good to cross-reference. Excuse me. In standard mapping, each timer has its own interrupt routing control. Allowed I/O APIC inputs are found by reading timer's capabilities register. All right. FSB mapping is not used. Registers. Okay. The following table and field descriptions can be found. Yep, offset means offset from the base address. That's all good as well. General capabilities and ID register. It might be good if we just try and read from that first. And then we're going to have to do some bit manipulation to grab all of this setting stuff. Encounter tip period in femtoseconds, 10 to the power of minus 15 seconds. Must not be 0, must not be less or equal to that, or 100 nanoseconds. That sounds like an insane tick speed. God help us putting logs. Well, we could log. We could update a variable from the ISR and then periodically log what the value of that is to see if it's counting. That would probably be a more sane approach to picking up that value. This bit is 1. HPET main counter is capable of operating 64-bit mode. The amount of timers -1 indicates which revision of the function is implemented. Must not be 0. Bit 63. 2 to 63 is reserved. Bit 0 overall enable. Main counter is halted. Timer interrupts are disabled. Main counter is running. Timer interrupts are allowed if enabled. Okay, so that's the enable mask. It's probably turned off. General interrupt status register. The functionality is dependent on whether edge or level triggered mode is used for the timer. I've seen that word before, edge and level triggered. Where have I seen that before now? If I look for the word edge, it's the I/O APIC. Set interrupt to be level triggered, not edge triggered. Edge triggered means when a transition changes. So it's probably the same concept. So we probably want level triggering. Edge triggered, this bit should be ignored. It should always be set to 0. All right, makes sense. Okay, that matches what I was just thinking about. Good, good, good. All right, the main counter value register. All right, so we know how to turn the timer on using that mask. That's all we know so far. And where the registers are. Bits 0 to 63 of this register are called the main counter value. Writes to this register should only be done when the counter is halted. Reads will read the current value of the main counter. 32-bit counters will always return 0 for the upper 32 bits. If the 32-bit reads are performed on a 64-bit counter, consult 2.47 of the spec. It's recommended to use 32-bit counters when on 32-bit only software. All right. So I think because we're running in 64-bit mode, we probably want to do this read here. All right, timer N configuration and capability register. So this is the address calculated here, here and here. Configuration and capability register, the comparator value register. Okay. So what's in the configuration and capability registers? Timer and interrupt routing capability. If the bit X is set in this field, it means that this timer can be mapped to the IRQ X line of the IO APIC. Bit X. Oh. So you can route it to any IRQ. All right. So as long as we don't tread on the toes of the PS2 IRQ, then we should be okay. That's FSB stuff, we don't care. This field indicates IOP routing. Allowed hours can be determined using the root cap. If an illegal value is written, then value read back from this field will not match the written value. Okay, so you can verify the rights on that. For 64-bit timers, if this field is set, the timer will be forced to work in 32-bit mode, otherwise it has no effect. This field is used to allow software to directly set periodic timers accumulator. Detailed explanation further in the article. If this is the size of the timer is 64-bit, otherwise it's 32-bit. Cool, so we can check the size cap. Timer supports periodic mode, enables a periodic timer, and writing 0 enables non-periodic mode. Setting this bit enables triggering of interrupts. Even if this bit is 0, this timer will be set. Okay. So that turns on interrupts for the specific timer. And then there's a overall timer enable. Okay. Initialization. All right. The following is the procedure you need to perform to initialize the main counter and comparators in order to receive interrupts. So, find the base address. Done. Calculate the frequency. F being frequency equals 10 to the power of 15 divided by the period. What's period? Counter clock period. Okay, save minimal tick either from the ACPI table or the configuration register. Minimal tick. We have that, right? We have you in the struct. Minimum tick. This structure needs to come into the header file because it's going to be it's shared. Okay. Initialize the comparators. What does that mean? Does that mean turning on the interrupts for the comparator? Wait, comparator value register. Used to compare with the main counter. Main counter tick period. There are bells going off inside my mind right now. So that is the resolution of the timer, which will scale the amount of interrupts per second, for example, you'll receive from that timer. Methinks. So if you wanted to, if you know the frequency of the timer, you could generate an interrupt at 1 per second. And that's what we would program in the comparator. Yeah, so initialize the comparators, set the enable flag to start firing the timer, and then there's a timer initialization. Determine if the timer N is periodic capable. Save that information to avoid rereading it every time. Why would I reread it every time? Once I know and I've initialized the timer, it's off it goes. Well, I'm guessing then that the most useful thing for me now would be to fire an interrupt every millisecond. So then if I was to try and measure things, I could have a millisecond counter and understand how many milliseconds have passed since I started recording where I started from, right? I think 1 tick is when the comparator value is reached by the main register. Yes, so if we, I don't know, saying that the main counter ticks once per second and you set the comparator to 10, you're going to get an interrupt in 10 seconds. But obviously it runs at a much higher frequency. So which is why at the top it's telling you to calculate the frequency. And I'm not quite sure how we do that yet. And I'm not quite sure what the minimum tick is. So steps 2 and 3, calculate the frequency function 10 to the power of 15 times period. Yeah. So I don't know where period comes into this. I'm guessing it might be assuming some knowledge of how timers are initialized, and because I'm a bit too new. So would I look at the main counter, for example? No, because I have no concept of time. So how can I possibly measure anything over a period? Keep in mind that allowed interrupt routings may be insane. Namely, you'll probably want to use some of the ISA interrupts, or at very least be able to use them at one point unambiguously. Last time I checked, VirtualBox allowed mappings for the HPET allowed every timer to be routed to any of the 32 I/O APIC inputs present on the system. Knowing how buggy hardware can be, I won't be too surprised if there exists a PC with HPET claiming that input number 31 is allowed, when there's only 24. Those limits are way beyond what we need. So I don't know if I should be paying attention to much of that warning. We just want to get a timer, a single timer up and running. So one-shot mode. If time is in femtoseconds from now to the interrupt, if time is less than the counter clock period, time is adjust time by time. Write to the register the timer configuration N. The I/O APIC input 9th bit, 2nd bit. And initializes the comparator, reads the main counter plus time. So that's setting the comparator into the future. Oh, I'm guessing the main counter then does not reset. Once it hits the comparator, it's just an increasing number. I hope the above is obvious. If not, please analyze the meaning of specific fields in the registers used above. Okay. And then periodic mode is just a bit more configuration on the comparator. Bit 2 is the same as above, interrupt enable. Bit 3 is also quite straightforward. One means a periodic timer, but we've also set bit 6 while. Let's take a look at the quote from the spec. Timer end value set. Software uses a read-write bit only for timers that have been set to periodic mode. By writing this bit to 1, the software is then allowed to directly set a periodic timer's accumulator. Software does not have to write this bit back to 0, it automatically clears. Software should not write a 1 to this bit position if the timer is set to non-periodic mode. This means that the next write to timer end comparator register will have the usual meaning, while the second next write will write directly to the accumulator. Oh, that's why I was confused by why there's 2 writes here to the same address. So one is writing to the accumulator and then the comparator. You could have code commented that, buddy. See, I'm so glad that I'm writing my own OS, because every time I come across like misrepresented documentation or code, I am definitely just going to stick the code in the source file to tell people why I'm doing why things are there, you know, and not leave it up to someone hunting down for a document. I need reasons. Okay, so I'm not feeling too bad about this. It's not too bad. The only thing I've got some questions around is the frequency and the period. But I've got a feeling that something's not clicking there yet, and it probably will do. Right? It doesn't feel too crazy. Is there any interrupt diagram starting from the quartz to the divider? Oh yeah, for sure. So in the official doc, we can jump back to this doc now, actually, and just compare. Where is it? Oh, here. Right, so this is the official documentation. Oh, counter clock period. Here we are. Oh, it's a setting in memory. There we go. This read-only field indicates the period at which the counter increments in femtoseconds, 10 to the power minus 15. A value of 0 in this field is not permitted. The value in this field must be less than or equal to. The resolution must be in femtoseconds rather than picoseconds in order to achieve a resolution of 50 ppm. This is all just register stuff again. Is this what you were after? This hardware diagram here? So there's a compare here, look, main counter to the comparator register. And then we go down to the IOA pick here and then cause an interrupt. Boop. So what's wild about this timer is there's 256 timers that you can configure. That's a lot of timers. Yeah, there's like that's the whole table of timers. The reason it gives you this calculation function is so you can turn on each timer, and then you can send each timer down a different IRQ if you wanted to. Got some experiences with STM32. I'm not familiar. I'm very new to OS dev, so you'll lose me quite quickly. Okay, so let's make a plan of action now. We've got some theory. It feels good. Nothing too scary about this. Got a bit of a question mark over the address that we've passed from the ACPI, so that might throw me off straight away. So what's the first thing that I can do? I can try and read from the main registers, which is the general capabilities. So the counter clock period, right? We need to grab that. We can check to see if we're in 64-bit mode just for fun, and then we can check the amount of timers too. So that's like this one, this, and this will be a good retrieval process to begin with. And again, I'm kind of scared that I won't be picking on the right memory location, so what I can double check though, that might be documented in the ACPI docs. Let's go and just double check that. HPET. Why are you not on here? Word hi isn't on here. What? Tables. There it is. Oh, it's called the IAPC, right? Oh no, it's probably going to link me to the document that I've just been looking at. ACPI component architecture, high precision event timer table. Yeah, it's taking me to an Intel PDF. That is probably the one that we've just been looking at. Yep. Lovely. What are the, let me just see, general capability and ID register addressing. Generic address structure format in the HPET table and up to 64 kilobyte timer block. Oh, that's the revision history. The BIOS reports the base address of the timer block via the ACPI tables and the ASL code. Base address can be 4K aligned. Memory mapped, 64-bit aligned, extensible, allows up to 32 times to be supported, capability trace of read-only. Wait. Is that a... Oh. Oh, I know what I've done wrong. I think I know why that address looks pretty weird. Let's go back to the HPET. Nope, not doing it there. We did it in the ACPI parsing. Yeah, that's the real address is here. Register bit offset, bit width. Okay, that makes me feel a bit better now. I was dumping the wrong value to the log. Failed desk has incomplete type. Oh, do I need to pull that down into the header now? I do. I should just put them all in eventually. Okay, so the address now definitely should look like something that is not in the higher half, and I need to cast it in there. Or throw it in there, should I say. That's better. So that address will be this. So that'll be the full address once it's put in the higher half of the kernel. I mean the memory map. All right, more confident now. I think I'm ready to do some reading from these locations. Yeah, these documents are a bit more verbose, which is nice if we need to dig a bit deeper from the OS Dev Wiki notes. What is the STM32, by the way? Oh, it's a chip, an ARM Cortex processor. Oh, it's a microcontroller. And how long have you been coding at the MCU level? This is my third month into 888 x86 OS programming. And I'm going to be a noob for many years to come, I think. Like, I can just see from a year from now that I'm just probably still not comfortable with multitasking cores or something, you know. It feels so deep, that knowledge base. 7 months, that's nice. All right, having a really good productive stream actually. We've already done that assembly refactoring, which I'm really pleased about how easy that was. Still feeling the effect of figuring that out. Very pleased. Okay, HPET initializing. Let's grab an address to do we want so API.h and then we're doing the HPT. Do we really need that code? I'm gonna move this into the HT to this module. Incomplete type is not allowed. I've got a feeling the IntelliSense has gone a bit screwy there. Yeah, we need to extend this pointer. That's my problem. All right, that guy shouldn't have a problem seeing that pointer now. All good. Do we get a compile? We do. Try cleaning up that parse function then. So we're not really parsing anything here. But once we've found the table, we can just save the pointer. Just make sure that refactor didn't break anything. Alright, HPET address, comparison count, count size, all good. Lovely jubbly. We're gonna get this address into the right location. So UINT 64. Apply the offset. That needs a mem. Grab that value. Okay, let's see if that looks correct now in the right location. Wait a second. Valid operand binary. Can I just do that and then cast? The same value. Let me just put those side by side. Really? All right, I guess it is. Yeah, I guess it's the right address. I guess we'll know when we start reading from the registers, though. So for that, we can just grab Address structure, description table header, the HPET. Right, we need to flesh out reading the registers. General capabilities and ID register. Why is there 8 of them though? Oh, 8 bytes for the 64 bits in this table. Okay, well that's simple. We've got this int 64 at this address. What shall I call this? Caps. Excuse me. Now we can just see if we can grab those settings from this variable. Okay, here's where my bit shifting is going to get flexed, and it's a rusty muscle. So please bear with me. Okay, exercise number 1. The amount of timers in bits 8 to 12. 0 to 7, 8 to 12. Alright, in theory, how would I do that? I'd bit shift the bits across and then apply a bit mask, right? Or can I just apply a bit mask to it anyway? But then how do I generate a bit mask for those bits that I want? So this one in particular is a bit interesting. It's 8 to 12 bits. Bits 8 to 12. So do I bit mask the whole 64-bit field to extract those bits out? You know what I'm saying? Because I can't do a 4-bit cast or something, so the best I can get is to shove those bits to the right side or the low side of the variable. But then I can't cast it into anything, so I need to mask. I may as well just create a mask for the 64-bit value to extract those bits. Which, off the top of my mind, I don't know how to create that mask. So, well, I would if I saw it on paper. I could just turn the 1s and 0s on that I want and then tally up what that mask equates to, but I can just use a calculator, right? Oh, so you still have to shift. You can't mask the entire... Oh, right, that's the easier way of doing it. Right, I could create a mask that just applies to the entire 64-bit value, right? Or we can just shift... and just put test here. We can say shift the caps over by 8 bits to get to our bit that we want. And then I need to blank what's on the left side after 12, right? So this is where I would and a bit mask. And again, that bit mask eludes me. Like, what would the bit mask be? Zero and F. Because the F means 4 bits, and then you're zeroing the bits after, right? Yeah. See, this. Sorry for my bad skills with bit masking. I've never had to do bit masking in my entire software career until I got to OS Dev. And now I'm like, I don't have a shortcut in my brain of how to create maskings. Oh, it's 1F for 5 bits. 8, 9, 10, 11, 12. Oh, right. Because 8 to 12 inclusive. So it's 5 bits that we want. So the F is the first 4 bits. The 1 is the next bit. To make 5 bits. Right, of course. Right, it's easy when I visualize it. It's just, how do you generate those? Is it something you just get used to and remember? I guess, right. I just haven't done it enough to remember. Like, I've got to think that 0x0f is just 4 bits and 0xff is 8 bits. Isn't it? Yeah. All right, let's try and amount of timers. All right. Let's see if we're in... This is going to verify if we're in the right memory location. Do I... I'm just thinking, do I mark that as volatile because it's a memory mapped location, or it doesn't matter? Because that there is performing the read. I guess it doesn't matter. Right, let's run. Okay. HPET num time is 2. Can we trust that? Bit 13 is the count size cap. Main counter is capable of operating 64-bit mode. If it's set to 1. Okay, that one should be easy, right? So that should be easy because in my head, that's just a single bit. And a single bit test is as simple as saying shift that over by 13 and 1, right? (64-bit mode is come back as 1. Okay. So I got to stand. I hope I didn't miss anything. No, just me talking to myself about bit shifting. Don't worry about it. Should be interpreted. Only to PCI's vendor ID. All right, this is a really interesting one. It's the 32 to 63 bits. Which is quite simple, actually, because we can cast this. You put this on my other monitor. Tick period. Yeah, we're just pushing it over by 32 bits and then leaving it to cast to a uint 32, right? Do I need to cast it manually though? I don't know. That might be enough. Tick period. Oop. Nice. Okay, that looks like a sane number. It's set to 10 million. All right, I'm feeling good about this. I've got a feeling that the only thing that's going to trip me up now is routing the timer to an IRQ and then catching that in I guess we can just set up the IDT ready for that, but we'll count size, num timers, general register configuration register. That's a 64-bit value. So we can set another. goes to the second 64-bit byte at that address, which arrives at the general config register. Bits 2 to 63 are reserved, but the first bit on here is the overall enable, what it calls the overall enable. So we'll just check that out. So we'll get the value from that address, and then we'll bit shift it over by, no, just and one. We're talking about the first bit. Which should be set to 0. And it is. And I can write to that bit to turn it on. And I bet if I did, we'd start getting interrupts down a certain IRQ. Shall we just turn that on and see what happens? Oh no, the timer interrupt would need to be enabled. So nothing should happen. Then there's the general, I can probably just put this into a struct, right? Config interrupt status. Wait, why does it say N? The main counter value register, where are you? This is read only. I can bring these over as well. This is read write. The interrupt status is a read write clear. That is 64-bit. Am I reading this correctly? General capabilities and ID. General configuration register, general interrupt status register. And where does the main counter value register live? Why is it jumped? Well, it's general. No, I don't need to bring those in. I can just read from this guy. Naming errors because you did not use a semicolon. Okay, if you say so. Let's change that to be called capabilities. It just reads a bit nicer. Okay, that should all mimic the same results. And it does. Comparative count, counter size, number of timers 2, 64-bit mode enabled. Tick period, overall enabled is disabled. Okay, we are good to go. That's nice to in a struct. And then suddenly, the main counter value register. Why bit 14 reserved? I'm going to check the official docs for this. I'm getting a bit confused over these memory addresses. That's my problem. Oh. There were some reserved bytes. Yeah, so the first 8 bytes is the 64-bit general capabilities, and the next 64-bit number in the next 8 bytes is all reserved, and they excluded that from the docs. So, which is why these addresses are kind of staggered. That just threw me off for a second. Do, 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 do. So the main counter value register. These are all volatile, by the way, because they're all registers. And we do not have control of that memory location when they're registers. Okay. But the pointer itself is not volatile, because that's just pointing to an address in memory. But the values are. Yep. Okay. So after the interrupt status register, the main counter value register. Yeah, I'm missing something here. So the next 64 bits are reserved, and after the config register, there's another batch of reserved. And there's a huge batch of reserved values after that interrupt status register. We might just have to pick that one ourselves manually. I guess we'll know for sure if that structure is correct once we start writing to turn on the timer. Okay. Make an entire struct volatile. The answer to that is yes. Okay, let's get the main counter value. This is going to be the most interesting value to read, actually. Like, we could grab this counter value register, enable the timers. We don't care about the interrupting. The timers would be running. And the main counter value will tick up. And then I can just dump that in the kernel and see if it's working. Ooh, I like that idea. That sounds juicy. Yeah, I'm definitely going to do that. But I'm going to grab some water. So I'll be back in a couple of minutes and then we'll look at doing that. Be. Sorry, I'm just making a coffee. I'll be a couple of more minutes, guys. So what I think I can do quite quickly. Hello again. Yeah, sorry. I'm thinking while the kettle is boiling. My kitchen is just literally a walk down here. Like I'm downstairs in my dining room. And I can hear the kettle. Software must not attempt to read or write across register boundaries. For example, a 32-bit access must be offset H4HH. Oh, I guess what it means there is that because you're like probably going to put stuff into a struct and you're going to read like a batch of bits off the registers, it doesn't want you misaligning reading from two registers at the same time, for example. Shouldn't write to read-only registers? Oh, shocker. Should not expect any particular or consistent value when reading reserved register or bits. That's no problem. Should perform read, modify, write operations on reserved bits. Host controls are not required to support excessive access mechanisms such as PCI lock. Okay, that's the coffee is ready to brew. Back in a second. Okay, got the coffee. Mm. Beautiful. Too bad you finished your tea. Yeah, I usually, like 9 out of 10 drinks I have are tea, and for suddenly now I just fancied a coffee. I get like that sometimes. Like certain periods of my day. But it doesn't affect me too much. I know coffee to a lot of people, really feel it, but it doesn't really affect me other than feeling very satisfying to taste. Mm. Okay, all we need to do now, is write the addressing function for the timer config. But we need to get access to this main counter register first. So, be right back text. Oh, you're right. I should check that. Sorry. Yeah, if we can just grab this guy, and then we're going to grab those two, the comparator and the configuration capability registers of timer 0, and then we'll just turn them on, right? We'll turn them on, and then we'll see if we get this main counter register counting up. So we'll just put those into some constants then. We'll do main HPET main counter reg. So this guy's at F0. And it's a 64-bit value. So it's a 64-bit value. We need to cast the address down to a char so that I can add this offset to it. Pointer arithmetic, right? So after enabling, you want to read twice and compare the values. Well, my first test will be just to see if the timer is online, right? So the main counter should be constantly counting. I think, because what depends is yeah, no, it should be constantly counting because your one-shot and periodic timer settings is on the timer configuration. And the only thing those timers are holding is a comparator value. Right? So the main counter, once it's online, should be constantly increasing, and then the configuration and the comparators on the individual timers are using comparisons against the main counter to fire an interrupt. So yeah, the main counter should be constantly increasing, and we can read that, I think, because it's at the register, right? So I should be able to just read it and check its value periodically. I think. Does that make sense? Like, I just want to turn things on and then just to see if there's numbers increasing and the timer is in operation. ultimately, after that, what we want to be doing is initializing the timer to be in a periodic mode and firing an interrupt, which will set up in the IDT. Which that shouldn't be too hard either, because we're just setting the comparator value. We'll turn on what IRQ that we want the timer to use, and then we'll enable the interrupt flag, and then everything should be fine. Makes sense in my head, and I'm getting happy that it sounds like it makes sense, because 4 hours ago, I was looking at this documentation thinking, oh my god, this is going to be horrible, right? This is scary stuff. But it's actually not that bad. So I'll be literally having a party if this works. I get so easily pleased by the things that I code on. All right. Let's do this. That's not a volatile variable because it's a pointer. The pointer itself is not volatile, but the value that it points to is. Does that make a difference? Like, do we care? No, because the only thing volatile does to the compiler is let it know what to optimize. So having a volatile pointer doesn't make any sense. So I only learned about the volatile keyword last night when I got bit by doing locking inside of an interrupt service routine. So I'm just kind of like understanding where that applies still. Like, it makes sense here because these values are pointing at memory mapped registers. It's a volatile data value. Okay, just for fun, let's try and print that value. So main counter reg, it's the value stored at that location. So that does a read. Only if you want direct access, but here you use offset. Yeah. Oh yeah, I want to cast this back to that address, but I want to do this arithmetic on the char. Useless type qualifier in an empty declaration. Excuse me? Useless type qualifier. Is it because it's unused? Is that the problem? Like, I'm reading from config, does it... It's just like, yo bro, you're not using these. Line 24. But then now I've got to mark all of these as volatile. Or is it? No. Oh, I think I understand what you're meaning now. I don't need to mark these as volatile because every time I read, it's going to the pointer address, right? Because I'm using pointers, it's not... You don't need to worry about it being volatile. Pointer and offset in the real address, right. I understand. But if you had a variable in a memory location, like, I don't know, where... Why would you... When would you ever not use a pointer? A fixed location. But you can't, like, set the location of a variable that you define. Unless you dereference a pointer, right? If you dereference a pointer... No, if you're dereferencing it, you're going to the address. Okay, problem for another day. Let's run this and dump this. All right, so the main counter is 0. Now what we could do if we really wanted to is enable the main counter, maybe. Like, can we enable it? And then even without the timers, will it start ticking? Would that be a thing? Overall enable. Okay, let's try it. Enable. And to enable this, I do regs config equals regs config or 1. Any initialization requirement before the enable? Let me just check, actually. I'm probably getting ahead of myself. So let's check the chat list. Find the address, calculate the frequency, save the minimal tick, initialize the comparators, set enable CNF bit, and then do your timer initialization. I'm enabling the timers only when I actually use them, so there's no real initialization of comparators. Yes, right. So you don't need to really initialize them unless you enable them. What I'm thinking from the overall design of this feature, this thing, is the second you open that overall enable, the main counter is going to start ticking. But we'll soon know because as soon as I enable this and try and read from that reg, even multiple times, right, it's going to have a different value. So even if I do this, as stupid as that is, it might show us different values. And it does! Oh my god! Let's go! Look at that! The main counter. Oh, this is exciting. That is sweet. Holy crap, that went up hell of a lot in the space of 4 lines of code. But that's what it's there for, right? It's a very high a high performant counter. Like a lot of resolution. Okay, well that's cool though. That is really cool. You know what I might do? And this is going to be... Please close your eyes when I do this. This is disgusting. Right? This is actually disgusting. If CNT is divisible by 50 million, then we're going to do a kprintf of the main counter reg. I think I've got a feeling when I was testing earlier that the amount of loops you can do in a second is around 50 million. So I'm just wondering if the main counter value comes anywhere close to this value that it reports. One, two, three, four, five, six. Yeah, that's 10 million though. Tick period. That might not be anything to do with the frequency though. What did we say about the frequency? Let me just try that though. I'm just very curious to see what the value is, how aggressive it is. And I bet, for a 64-bit value, that's gonna... What's the maximum of a 64-bit value actually? It's pretty huge. Yeah, I wonder how long that can run for. Oh, it's gone negative. Interesting. So it does a wraparound. Make none once, just read twice. What do you mean, sorry? Do you mean just 2 prints on the register and see what the difference is? Um, makes no sense. Yeah, no, I was just curious there to understanding if that value how it behaved. There's no logic to building off this. Um, I guess we're going to pick on the timer now. This is where the it's so faster than a single instruction. Yeah, yeah, of course. Um, so if I get two writes from that memory location, one after another, you'll see the difference. So it started on 92 and then reached up to 1.5 million between two instructions. That is insane, right? Because just thinking about how fast instructions are executed on a CPU, and then there's another distance that happened between two instructions by that amount. Like, what? Oh, you mean, do you want to read from it twice like this? Is that what you want? Surely that's not going to work. Oh, I know what the problem was between two instructions. No, I'm thinking of assembly. No, it had all the function call stuff. It's not instruction. I'm talking out of my ass. Yeah, that resolved to 0 twice. Um, kprintf, 200 instructions, and here the compiler optimized the read. Yeah, I think you would have to do that in assembly, wouldn't you? To see the difference, truly see the difference. But it's kind of like a fruitless exercise now because what we want to do is get it to a point of having time. Like, I want to know when 1 second has passed. And then I want to know how I want to know the resolution in milliseconds at my absolute detail. Like, I don't care anything more than that at the moment. I mean, I will do eventually, I guess. You know, am I missing something from what I'm reading in the docs about the frequency and the minimum ticks and stuff? Like, what is that? Like, this reader-only field indicates the period at which the counter increments in femtoseconds. What's ppm? All right, let's continue forward. And enable a timer, right? So let's get a timer going. And let's get the interrupt firing, right? And then once we've got that, let's try and control it so that we get an interrupt per second. And then once we've got to that point, we're kind of in control of time. But until then, nothing's making sense right now. Where's the OS wiki page? I keep losing my way. That's the SDM. Here it is. So periodic mode is what we want, right? So it's just these three lines. But we've got to set up the IDT and the IRQ routing. Counter clock period. If time is in femtoseconds from now to interrupt. Is that the resolution? Is like, am I being stupid by it telling me that it's in femtoseconds? Is that the resolution of the counter? I mean, if I flip that and said time is in seconds from now to interrupt, then that makes more sense, right? Okay. Let's grab these addresses. Timer and configuration and capability register. All right, where is the memory location of this? It's a 0100 plus 020 times n minus up to. Without calc, 1 second interrupt is not possible. Right. So, but there has to be, right? You must be able to control the resolution with the comparator. Like, what value do you put in the comparator that controls the resolution of your interrupt? And in the capabilities, what is the tick period? Which here is this. So this is another interesting statement. Calculate the HPET frequency, which is 10 to the power of 15 over period. What is period? Okay, getting distracted. Let me get into the timer. Let's get this interrupt going. And let's get a value into the comparator and then start worrying about resolutions. Right, let me go and reserve that timer vector actually. I'm going to bump this up. My timer is now on 32. Oh. I just realized something. My assembly solution to handling a interrupt does not lend itself to any interrupt vector because it's hardwired to that function. So that's actually not in a good state. And I'll need to modify that to manage all the interrupt vectors. But I'm going to call this handle timer. And I'll do ISR save, ISR restore. And then we need a Lapic EOI as well. And then we'll set up the vector. And we'll put that on handle timer. All right, that's the interrupt vector setup. And now we need a function for calculating the address of a timer. So that's got the base address at the global level. Now we can define how are we going to return this? Maybe a pointer? A uint64 pointer? Because that's what all the stuff's aligned to. Maybe. Timer config reg. And then this will be the timer number that you want. And then we'll have another location, which is the comparator. And again, we'll take in the timer number that you want. So calculations for the timer reg is in the wiki. We want gonna return. We need to get the base address into a char format. Configuration and capability register. General capabilities and IG register. General interrupt status. Timer configuration capabilities register. 64-bit. Ooh. Plus 20. Just write it out and then hope for the best. So the comparator reg comes in at 0108. Not sure what this offset's for. Timer comparator, what are you? You're in 64-bit, okay. Maybe size of a timer block. Yeah. Like the whole data related to that timer in memory. That would make sense actually, right? And then just your registers for getting into the config and the comparators are at the top. And then there's like a bunch of reserved memory area after the timer. Am I even using this? I am. Let's just put that there because that's kind of obvious. So we can get the timer config. So what are we configuring? General interrupt status register. The general interrupt status register, I don't think we need to deal with. The functionality is dependent on whether edge or level trigger mode is used for timer N. When a corresponding timer interrupt is active, this bit is set. Oh, it's an interrupt flag. Which acts as like a lock for when an interrupt. Software can clear it by writing 1 to the bit. Does that mean we need to clear it when we're handling a timer? It doesn't mention that in the initialization. And it doesn't do it in the code. So I guess not. Status register is, yeah, it's just an information. I like how you said it's information, not info. I mean, it's info, not control. Like that distinction, it's giving me a different way of saying it in my head. Right. Timer interrupt routing capability. If bit X is set in this field, it means that this timer can be mapped to an IRQ line. The IOA pick. 32 IRQs. Redirect IRQ. Apply an override to the specified IRQ, taking into account the interrupt service overrides contained in the specified APIC. Inside of one block, a timer need to be filled correctly, plus some extra external registers to inform that the timer N is interrupt enable. There was an interrupt enable somewhere. Sending this bit 1 enables triggering of interrupts. Yeah, it's here. It's bit 2. And we'll need to set that to turn on the interrupt firing. So that chooses the IRQ that it goes down. And then once we've chosen an IRQ, we need to call into the IOA pick here and redirect the IRQ to a vector in the IDT. And that's what will route it to our function that we set up. Now, what IRQ do we give it, though? Because obviously there's reserved IRQs. So it's like, you know, which one do you choose? Like, as far as I'm aware, the keyboard is going down IRQ 0. No, IRQ 1. Keyboard's on IRQ 1. So I guess we could put the timer on IRQ 2. Yeah, I think I can take it from... I can do the interrupt routing, that's fine. and that's what I need to do now. I just need to see the interrupt firing for the timer, and then we can worry about the comparator settings. So I need to focus up here because this should be easy to do, but I just keep losing focus on thinking about it. So if I set 32-bit, that will go on IRQ 0. If I set 33, it'll go on IRQ 1, and if I set 34, it'll go on IRQ 2. All right, let's make a shopping list. Let's make a shopping list. Set IRQ for timer N. This field indicates the IO APIC routing. Allowed values can be determined using root cap. If an illegal value is written, then value back. What does that mean? This value indicates IO APIC routing. In root capabilities. Bits 9 to 13. If the 64-bit timer field is set, the timer will be forced to work in 32-bit mode, or otherwise it has no effect. It's very used to allow software to already set period on its accumulator. To set periodic timer's accumulator. Do I care about the accumulator? I think so. Read only bit set to 1, read only bit, this time supports periodic mode. I guess we should check that before trying to set up periodic mode with it, maybe. Okay. Writing 1 to this field enables periodic timer, and writing 0 enables periodic mode. Oh, non-periodic mode. Okay. Variant cap is 1, then writing 1 to this enables. Okay, enable periodic timer. So this Bit 1 enables triggering of interrupts. Enable interrupts. I don't know if we need to set this, but maybe we do. Sometimes they're not capable of periodic interrupt. Yeah, I'm guessing you can for loop through them. Because you know how many there are. We've got num timers here. So I bet you would... I'm assuming that all the timers are periodic enabled, but maybe on some systems they're not all periodic enabled. And we'll certainly report on that, right? We want to make sure that we are definitely periodic enabled. And then if we're not, then I'll probably just look at the next timer ahead and see if that one's periodic. And it might be a system setup thing. Enable periodic timer. Let's do another thing here. Check periodic support. Is this an actual writable value or not? I'm kind of confused. This timer generates edge interrupts. This timer generates level interrupts. When the interrupt is generated, the status is set. If another interrupt occurs when the bit is cleared, the interrupt will remain active. Like, is that... Can I write to that? It's configuration. We'll try doing that. That level interrupt mode. Yeah, the whole thing is a configuration 64-bit block, so and it specifically says here if it's a read-only bit. Da, 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 da. Five is not, yeah. So is 4. So, okay, and that's an easy write, right? That's just a 64-bit value being written to say what our value needs to be compared to the main counter value to trigger an interrupt. Yes, some timers are not 64-bit on a 32-bit system. So we're on a 64-bit CPU, so we're 64-bit. We dumped that in the log too. Dare I say you might have 32-bit timers on a 64-bit system? If you do, then you could write a 32-bit version of your code, because most of this is 32-bit. But yeah, in the logs, it was telling us we're in 64-bit timers here, like 64-bit mode. But that's on the emulator, you're right. If I was on real hardware, maybe we might be dealing with a 32-bit timer. Feels weird though, right? You've got a 64-bit CPU and you have a 32-bit high performance timer. Like what? What under what circumstance would that be? Normal cases in all MTUs. Okay, sorry. I have somebody DMing me on Discord. Saying that they've accidentally reported my account for fraud, my Discord account. And I've got a feeling it's either a bot or someone that's trying to phish me. So this conversation has gone something like, "Hi, I've accidentally reported your account for fraud. Can you help contact support and let them know that it's a mistake?" And I'm like, well, I haven't done anything, so if they want to check my account, they'll see that I'm fine. And now they're like, well, you still need to action something within 48 hours or your account might be banned. And now I'm like, okay, what do you want me to do? And now I'm expecting a phishing link. And then I'll be like, ah, there it is. And I've no idea who this person is. They're a mutual on the OS Dev Discord. But it's very suspicious. It's getting a bit silly now. Okay, right. Let's hammer down our shopping list of things to do. I'm being delayed here. Oh, actually, it's not even that late. It's only 7 p.m. here. We've got loads of time. If I shall declare, I will not end the stream until we have a timer running. An interruptible timer, that is. Okay, I'm just rearranging my windows on my other monitor. That's ChatGPT, OBS. Yes, with a correct interrupt period. So I'm hoping so, right? I think we have enough information to understand a passage of specific time, frequencies, tick counts. Da, 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 da. All right, let's lock and load. Okay. HPET. Set the IRQ for timer N. So let's first grab the config reg. Timer config register for timer 0. Okay. Timer config. We could report the values off the register first. Yeah, let's try that actually. HPET timer 0. And this will be bit 4. So timer config bit. Would it be better to just read the whole reg? Like this? No. Actually, that would be a bad idea because of volatile data. A bit field struct makes things easy to read individual bits. I've never seen a bit field struct. Can you do that? Oh, is that where I've seen people like put :5 here? Does that mean something? Oh, you mean shifting. Okay. Sorry, I'm losing my way here. Periodic mode. Or and then there's another one, the 64-bit mode. This is bit 5. So yeah, we've got a periodic mode set to 1. We've got a 64-bit mode set to 1. You know what? I should delay that enable after we've done the timer. Feels weird to not do the configuration first and then let the timer fire. Or else you might get an immediate fire of the timer you've enabled periodically. Alright, so we've done check periodic support. Now we need to enable the periodic mode. Wait, enable periodic timer. Does that mean I wouldn't? That wasn't enable. That was the support stuff. Right. Set the IRQ. This is what we're doing now. So we're going to send this down. We're going to use IRQ2. Zero would be bit 32, 1 would be bit 33, 2 would be bit 34. Timer config equals why would it 1 left shifted by IRQ? Thank you for the follow, Mr. Colonel. So starting with the 64-bit variable, and I want to turn on bit 34. Why can't I not figure that out? My bit math is terrible. So you can create a bit mask by shoving the value 1 left 33 times. Now, what happens to the other bits though? They're going to be on 0, right? Oh, but if you're ORing, you're merging the bit values. It's not equals, yeah, I'm ORing the value. Left shift count is greater than equal to the width of the type. Excuse me? Must not have more than one interrupt by a timer. You could do, though. You can set a different IRQ for a different timer. Because it's just sending it to the local, not to the local, but it's sending it to the IO APIC. All right. Documents. Timer interrupt, read only bit. Bit is set to 1 as we use FS. Interrupt mapping, don't want that. Don't need that. If this field is used to allow software to set accumulator. This field is used to allow software to directly set periodic timers accumulator. Detailed explanation is provided further in the article. Oh, that's where you do a double write. I need to set bit 3. I don't need that cast because of the one unsigned long value. So bit 3 is enabling the periodic timer mode. Enabling interrupts is on bit 2. I should be able to just do this in one line, shouldn't I? I can just OR all of these together. But whatever. And then setting the level interrupt mode is on bit 1. I wonder what... I could just convert all of that into a decimal value, couldn't I? And then fire that as the OR onto the timer config. But that would be meh for code readability purposes. All right, I think that's fine now. Set level interrupt mode, triggering of interrupts to... I think once we turn this bit on, it's going to start firing input. Well, after we do this overall enable. So this guy... Now, here's where we're kind of a bit stuck, because we don't know what our comparator needs to be set to. Now, I am going to go ahead here and just randomly assign the tick period. And I don't know why, I just want to pick that number, right? I mean, that is a high number, it's like 10 million, but I want to see what it behaves like. So we've set everything. Did we call the IRQ override? Did I do that? We've got the IDT, but did I do the override? Don't think I did. Let's just search. Keyboard vector. No, I didn't. Okay, well, let's do that. It's in the IO APIC. So BSP LAPIC ID is in CPUI.h, which is the bootstrap processor. Comparative register size. Right, if we're in 32-bit mode, you've got a 32-bit comparator, but this is in 64-bit mode, so we've got a 64-bit comparator. which is why I'm just setting it there. Because we've got a uint 64. We're setting that whole register in one fell swoop. Okay, so BSP, LAPIC ID, the vector number is the timer vector, which is in the IDT. And then IRQ that we set was 2. What did I set for status? True. Oh, that's a mask. Yeah. That's like enabling the override. Okay, so that sets up the IRQ handler in the IDT. And that hopefully works to say that we want IRQ2. 0, 1, 2. Yeah. Okay. And then boom, we enable. So what we're going to experience here now is if it's working, we're going to get a tick in this function here. Let's just new line that. So let's run this and fingers crossed. God damn, if this works, this would be amazing. Bingo. Amazing. Holy shit, I am so pleased. I can't believe we just one-shot that. Holy crap, we just literally just one-shot that entire solution. Just like bam, 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 straight from the documents. That is amazing. But what we cannot fathom now is to what resolution is our ticking, you know? To what resolution? Um, Another problem I have is when I route the logging to my terminal, I get delays, like it holds up the interrupt handling, which is why when you saw me run it, it produces like a bit of a stuttering effect, and that's a bug in my terminal code. So main can take 100 unit every tick period and interrupt fired if main continue to compare, so 100 unit times value in comparison. Okay, I'm asking GPT because it's got the docs around this, and I want it to kind of break down why I'm not getting it. You need to understand a few key details about how HPET works. The timer runs at a specific frequency, which is provided by the main counter that increments at a rate determined by this frequency. This frequency is typically stored in the general capabilities and ID register and tells you how many times the main counter increments in 1 second. To make an interrupt fire once per second, you'll need to perform the following steps. Read the frequency. Determine the frequency from the HP general capabilities and ID register. Now, the general capabilities, the main counter tip period in femtoseconds, counter clock period, did that. The value you need to put in the comparator is essentially the value of the frequency, and that's what I did. This is because you want the interrupt to fire once every time the main counter increments by an amount equal to the frequency, which happens once per second. So, read the frequency from the HPET general capabilities and ID register. The value is not the frequency itself, but a number from which you can calculate the frequency. The register contains a value that represents the period in 1e minus 15 seconds per increment. To get the frequency, you calculate 1e15 over period in femtoseconds. What does that mean? Your frequency, for example, is 10 megahertz. That means the main counter increments 10 million times per second. To have an interrupt once per second, you set the comparator increment by 10 million. Sure. That doesn't equate in my mind. Timer, tick period, 1e over 5 over the tick period. SSE register return with SSE disabled. No! Oh no. So that's a compiler level thing, but would you really want that on your kernel? It's questionable. Oh, so the const. It's actually a constant number. Nope, that is definitely not 1 per second. Oops, I just accidentally did my text-to-speech. Yeah, this logic doesn't obviously marry up with what's happening. But this document says 10 to the power. I don't know, really. Like, shall I have a look in these documents? Maybe there's a different explanation. You can also write to the comparator's match register to select a different period. A write to the register will not immediately be loaded into the comparator. It will only be loaded at the time the comparator triggers. Okay, there's no mechanisms to immediately change the periodic rate. Oh, we're not doing this. We might be getting continuous interrupts. Tick divided by... Wait, have I misread? That's a crazy number. Yeah, that's not any different, but I'm concerned about not doing this. So this is kind of like the LPIC. You need to kind of like acknowledge the interrupt. Just noticed actually, maybe put underscores on those. So let's just do HPET AC int n. Well, you went 32. And then we'll do so to acknowledge, if a timer has been configured to a level triggered mode, which we are, then its interrupt must be cleared by the software. This is done by reading the interrupt status register and writing a 1 back to the bit position for the interrupt to be cleared. Which is in that flag. Base address. So interrupt status. And then bits 32 to 63 are reserved. Bit 0, bit 1. So I need to write 1 to this bit. So the bit is 1, 2. Wait, what IRQ did we choose? So it's 3, I think. Let's not take a timer number because that doesn't make any difference. Um, 32, 33, 34. Yeah, it's the third bit. Oh, you mean... I'm losing myself. Ugh. I think I've been focusing for too many hours. My brain is running out of juice. If I OR against 1, you're doing 0. So that's bit 0, that's bit 1, that's bit 2, right? But that doesn't correspond to what I was doing up here. No, that's right. That is correct. What am I thinking? Okay. It all makes sense. Again, it's just my lack of bit shifting experience. Oh, I need to wire that up to the ACK call. Needs to be in the IDTC, I believe. Turn it back. What, to 3? Oh, divide. I knew this was going to be kind of like a lot of trial and error kind of stuff. Yeah, it's going crazy. I wonder if no, there's got to be something wrong because if we times that by the tick period, that's such a humongous number. So something's not quite right at all. Yeah, there's something pretty off here. Can you do that in C? I know you can do it in other languages. Oops, actually, it is divide by. Yeah, there's just something really killing it. Like, it doesn't make any sense. Why it's firing so many interrupts. Hmm. I might. Do I try and solve it now, or shall I eat and then solve it? Like, we might not be writing to the right comparator reg. But that can't be right, can it? Like, if that was the case, then if I didn't enable interrupts on the timer, then these timer interrupts shouldn't run. That would validate my memory address. Ah, well, yes, that's a problem. For example, if I don't set the IRQ, I don't enable interrupts, right? Like, there's no way that interrupt should be firing. Oh! You know what's happening? That IRQ is the mouse. As I was moving the mouse, the ticks were firing. Okay. That's funny. That is really funny. So we have got to pick a different IRQ. And this is what I was concerned about. I'm like, how do I know what IRQ I'm supposed to use? Like, I might be treading on someone's toes, if not now, maybe in the future. Like when I start doing things with other devices and they start interrupting on that IRQ channel. But that's probably something I can Google. All right, let's bump it up. Where's the IRQ stuff? So IRQ2. So we'll go one more. 35. Enable interrupts. Set the comparator. Divide by. Set the handler. IRQ3. And then enable. And now that goes up one because we're picking on the next IRQ bit. All right, give that a go. Okay, so we're not getting any interrupts now. Did I mess something up? Timer vector, that didn't change. That's just the entry in the IDT. But we're overriding that IRQ. Let's double check these things. What? IO APIC? No, that's the LAPIC. Glitch cat. So let's try setting the comparator really low. Right, so let's just go with tick period for, well, let me just put the value 1 in there. Oh, but you're not allowed to go, there's a minimum. I don't know, let's do 1,000,000. Try and get it to fire as often as we can. Alright, we can see the log line in there for applied and IO APEC redirect on vector 33 GSI1. Maybe let's try bumping up the IRQ. GSI4. Just the global service interrupt for that sets a low comparator, that sets the interrupt mode, that enables the interrupts, that's periodic timer mode. It's hard to know, like, because there's no validation, right? Determine allowed interrupt routing for current timer and allocate an interrupt for it. Keep in mind that allowed interrupt routing may be insane. Yeah, maybe, I don't know, we need to probably double check and triple check everything we've written in terms of what we're enabling on the config bits. But I want to go get some food. I've been streaming for 5 hours now. So I'm going to get some food and then chill out for the rest of the evening. But I'm glad we got this far. I'm glad we kind of like we've got the code in there, you know? Like it's all in there. We know what we're dealing with. We've just got to bug fix and iron it out. So yeah. So yeah, I've got a lot of time off work in the next few weeks, so I will be streaming a lot. You'll have to catch me when I'm streaming. But yeah, thanks for staying here, Neg. That's nice of you to help as well. So fingers crossed next time we get the timers firing correctly. But yeah, thanks for watching. Have a nice evening wherever you are, morning, evening, or afternoon, and I will see you soon.